Chapter 6.2, number 53. We're asked to find the volume of a tetrahedron with 3 mutually perpendicular faces and 3 mutually perpendicular edges with lengths of 3 centimeters, 4 centimeters, and 5 centimeters. Stated simply in our problem statement, we can say, find the volume of the irregular tetrahedron that has edge lengths of 3, 4, and 5 centimeters. The reason we say irregular tetrahedron is because it is not like a typical one as seen here. We have no assumptions because this is a basic problem. Formulation. We are looking for V, the volume of the tetrahedron. A is the area of the triangle cross-section. If we look at our figure and we cut out a thin slice through the middle, we would get a shape such as so. The area of this triangle is given as half base times height, where height is the height of the triangle cross-section and B is the base of the triangle cross-section. Z is the height of the tetrahedron, and it is variable. Methodology. The first step is to find similar triangles to find the values for B and H in terms of Z. The reason we find it in terms of Z is because this cross-section is so thin because it is shrinking along the Z-axis. That is why we would like to find it in terms of Z. Next, we use the definition of volume on page 439, which gives us this equation. The fundamental theorem of calculus, part 2 on page 398, which gives us this equation. The area of a triangle on reference page 1, as so. To set up the formula for the volume of the tetrahedron, the next step would be to use the substitution rule on page 413, as seen here, to simplify the equation. Lastly, we would use the general antiderivative laws on reference page 5, as seen here, to solve out the rest of the integral. Now let us find the results. Drawing out the tetrahedron will help us to visualize the problem better. As we can see from our three-dimensional figure, the length here is 3 centimeters. The length here is 4 centimeters. And the height here is 5 centimeters. We can also draw in our cross-section. Where this is H and this is B. This is the X, the Y, and the Z axis. And as we can see, this green triangle may move up or down the Z axis. The first step was to use similar triangles to find the values for b and h in terms of z. As we can see, this triangle is the same as the one seen in the picture, where area equals half base times height. But like mentioned before, we need to find base and height in terms of z. We can do this using similar triangles. So first we will pull out this purple triangle here. And the green cross section here was h. We want to find h in terms of z. Now, this line here is the z-axis. So we can say that this here is a variable height of z. We also know that the full length of this is 5 centimeters. The bottom here is 3 centimeters. Therefore, the remainder of here would be 5 minus z. Now we can use similar triangles. We can use this triangle here and this triangle here to find the area. So 3 is to 5 as h is to 5 minus z. Solving this out, h equals 3 over 5 minus z. Now we have h in terms of z. Next, let's find b for the orange triangle. We know that this length here is again 5. And this height here is a variable z along the z-axis. And this is 5 minus whatever z there is. We also know that this length here is 4. We can now use the similar triangles. 4 is to 5 as b is to 5 over z, 5 minus z. Solving this out, we get that b is equal to 4 over 5 times 5 minus z. We now have h and b in terms of z, and we are ready to use the volume equation, the definition of volume, to find the volume of this figure. V equals the integral, some integral, of the area function we have here in terms of z, which we found, in changing z. This integral here is from 0 to 5 because this triangle can shrink or grow up and down along the z-axis, with the limit being 0 and 5. So we will go 0 and 5. Volume equals 0 to 5. Area was half BH dz. Since there's a z here, we need b and h in terms of z, which we found, which we may plug in now. B we found was 4 over 5 minus z. And h we found as 3 over 5 minus z dz. let's pull out these constants. Volume equals 12 over 50. Excuse me, we need a half here. Half times 4 over 5 times 3 over 5 will give 12 over 5. The integral from 0 to 5 of 5 minus z squared, dz. We can now use the substitution rule to simplify this equation. Let's pull out 5 minus z. We will say that u equals 5 minus z. Therefore, du equals negative dz. We would like to swap out these dz's. So we go dz equals negative du. We will also need to change these limits. So u of 0 equals 5. 5 minus 0 is 5. And u of 5 here will change to 5 minus 5 is 0. So our new volume equation, volume equals, we're going to exchange this dz for negative du. So let's pull this negative sign in front of our 12 over 50, which simplifies to 6 over 25. Integral, the new integral, now from 5 to 0, u squared, and this dz is being replaced with du. We can now use the antiderivative laws to solve out the rest of the integral. Volume equals negative 6 over 25. U squared, the antiderivative, will be u cubed over 3 from 5 to 0. This gives us volume equals negative 6 over 25. Plugging in 0 will give us 0. 0 divided by 3. Minus, plugging in 5, 125 divided by 3. Volume equals negative 6 over 25 minus 125 over 3. Or negative 125 over 3. Multiplying these two values will give us 30 over 10 equals 30 over 3, which is 10 centimeters cubed. And this is our final answer. 10 cubic centimeters is the volume of this figure shown here.